Hello PhysChem crew, hope you're all doing well. We've been looking at freefall the last couple of days. You got to do a little lab at your house. I got to watch a few videos yesterday. Today we're going to actually do a few problems. So we're going to walk you through some stuff to do. First thing we need to do though is kind of define what does freefall actually mean. So an object is in freefall under these criteria. So an object freefall has no wings, so it can't be a bird or an airplane. No thrust, so again, no airplane, no helicopters. Parachutes, no parachutes. Or contact with the ground. That's going to be our definition of free fall. So it doesn't have any wings, no thrust, no parachute, no contact with the ground. So it's just an object that's in the air. Think of a ball that you've thrown upward while it's not touching your hand and hasn't landed yet. That time it's in the air, it's in what we call a state of free fall. On Earth, objects have the same acceleration no matter what their mass is. So on Earth, the acceleration of all objects in free fall is, we're going to approximate it to be negative 10 meters per second squared. In reality it's negative 9.8, but we're going to make the math a little bit easier and eliminate some of the decimal point stuff and just round it to negative 10, which is a pretty good approximation. As you've seen both in the lab and those videos from yesterday, this value assumes there's no air resistance, which for most of our problems we're just going to assume that things don't have a terribly high amount of air resistance. We're not dropping pieces of paper. We're typically dropping a rock or a ball or something like that. So we can assume that negative 10 meters per second squared for everything. And that number is specific to Earth. If you've seen footage, which if you did your homework yesterday, of people on the moon, they're bouncing around. They just take a step and they don't walk like they do on Earth. They kind of bounce around. That's because the acceleration on the moon is significantly less than it is here. In fact, on the moon, this value is approximately negative 1.6 meters per second squared. So it's about 1/6 the amount of acceleration. If you go to Mars, which is a planet similar in size to the Earth, a little bit smaller, it's negative, just about a little less than 4. We'll just call it negative 4 meters per second squared. Venus, which is the most Earth-like planet in our solar system in size, very close, negative 9 meters per second squared. So if you were walking around on Venus, assuming you hadn't melted because it's extremely hot, the hottest planet, it would feel like you're walking on Earth. You'd need a really, really thick spacesuit, so you'd probably be feeling the weight of that, but it would feel as close to Earth as you could get. Let's do a quick little example here. Let's say you've got your hand and you're holding a ball of some kind, and you're going to drop this ball, and we have a super high speed camera that's watching the ball fall and making position time and velocity time graphs of the ball while it falls. In the first second that the ball falls, it falls this certain amount of distance here. We'll just draw it with an arrow. In the next second, it falls a little more. Next second falls a little more. So on and so forth. Every second it's going to fall further because it's accelerating. It's going faster and faster as it moves down. Now if we made a position time graph for this ball that we're dropping, it needs to speed up and it's falling down. Down is universally as the negative direction. So it starts at 0, 0 and it's speeding up in the negative direction. As far as the velocity time graph goes, it starts from rest, so 0 velocity, and it speeds up again in the negative direction. So it just has a negative slope. And what would that slope be? Well, the slope here represents the acceleration. Which is negative 10. Now, again, we were talking about this high-speed camera. If these were 1 second intervals, 1 second, 2 seconds, 3 seconds, this acceleration of negative 10 is important. Look at what the units are. It's meters per second, which means after falling for 1 second, your object is now moving at negative 10 meters per second. A whole second later, and it's had another second to speed up by a unit of 10. So at the 2 second mark, your velocity is negative 20 meters per second. At the 3 second mark, your velocity is negative 30 meters per second. So you can see how things can get going really, really fast in a relatively short amount of time. Let's do one more example. You got a person standing at the edge of a cliff holding a ball. And they're going to drop it and let it fall all the way to the bottom. And we're going to say that the ball lands after 3 seconds. Question A is, how far did the ball fall? So we're going to start to bring back those kinematic equations, and I had in the survey that I put out last week, some folks wanted me to kind of recover those and talk specifically about what the variables mean, so let's do that right now. We had two equations. We had delta x equals VIT plus 1/2 AT squared. What does delta x represent? Displacement, how far something moves from where it starts. VI, that's how fast something is moving at the very beginning of the problem. T stands for time. It appears twice in this equation. Once here, once here. A is your acceleration of your object. If we're talking free fall, it's always negative 10 for Earth. Our other equation we have is VF equals VI plus A times T. VF is the velocity of the object at the end of the problem. VI is the velocity of the object at the beginning of the problem. A is your acceleration. Again, for free fall, it would be negative 10 for Earth. And T is your time. Time is measured in seconds. Acceleration is meters per second squared. Velocities are meters per second. And displacements are measured in meters. Looking at part A, if we're asked for something, how far, that means we automatically are going to use our equation that has delta x in it, because delta x tells us how far it falls, or how far it moves. So delta x equals VI times T plus 1/2 times A times T squared. For this particular problem, since you are just dropping the ball, it has an initial velocity of 0 times 3 for a time, plus 1/2. It's in free fall on Earth, so negative 10 for A. And then you have the time again squared. So simplifying, got 0 plus 1/2 times negative 10 times 9. So negative 90 times 1/2 is negative 45 meters. So our ball fell 45 meters. This negative sign just means that it fell downward. It lands on the ground 45 meters below where it was let go from. So our answer to A, it falls 45 meters. Question B, how fast will the ball be moving when it lands? Okay, so we're looking for a final velocity. We have an equation that has final velocity in it. We've got Vf equals Vi plus A times T. We're looking for the final velocity. The initial velocity, again, we just let it go, the rock. Right, a little Frozen reference there for those paying attention. So the initial velocity then is 0. Acceleration, negative 10, because it's in free fall. And it lands 3 seconds later. So what's our final velocity? Negative 30 meters per second. Of course, you could have done that in your head because we know its acceleration is negative 10. So after 1 second, it's going negative 10 meters per second. After 2, it's negative 20. So after 3, it's negative 30.